In this video, we discuss degradation mechanisms in thin film PV. PV modules have a very long lifespan, but it is still important to study failure mechanisms with the aim to improve reliability. Several degradation mechanisms of two types of commercially available thin film PV technologies will be discussed: CIGS and amorphous silicon PV. For CIGS, different failure mechanisms and causes have been identified. An increase in resistance losses, both series and shunt resistance, can be caused by water ingress. The material and interface quality can be decreased due to alkali migration from the glass. Alkali migration can also lead to potentially induced degradation, in short PID. Worm-like defects can be formed in reverse bias, caused by partial shading, and resulting in local shunt paths. In the next slides, we will present more details. Failure aspects in the module, for example delamination, are similar to silicon PV and have been discussed in previous lecture. Here we show the device structure of a CIGS solar cell. The sketch shows, from bottom to top, the substrate, molybdenum and selenized molybdenum films, the CIGS absorber, the cadmium sulfide buffer layer, and a contact layer and a TCO layer. All these individual layers can face moisture-induced degradation. When molybdenum and selenized molybdenum films are exposed to water and oxygen, black and blue stains can occur at the metallic molybdenum surface, especially under elevated temperatures. These stains contain molybdenum oxide, which is generally badly conducting and reflecting, and will result in a higher series resistance and a lower current respectively. For the CIGS absorber material, CIGS grains themselves are more or less intrinsically stable. When exposed to damp heat, thus moisture, material changes may occur at the grain boundaries and at the interfaces to the other layers. It is assumed that hydrolysis or oxidation will lead to degradation, and sodium may enhance the oxidation effect. Other studies have also proven that sodium can largely impact the stability of the absorber layer. For the cadmium sulfide buffer layer, diffusion of cadmium and sulfur into the adjacent layers and chemical reactions at the interfaces could occur under damp heat condition, resulting in performance degradation of the solar cell. For the TCO layer, the stability could be influenced by ion migration, material decomposition, and interactive reactions at the adjacent layers, such as the cadmium sulfide buffer layer. Numerous investigations have been reported regarding the TCO stability issue. Basically, the stability of the commonly utilized aluminum-doped zinc oxide, or AZO, is not optimal. Replacing it with tin-doped indium oxide, or ITO, notably improves the stability of the cell. Fluorine-doped tin oxide, or FTO, is reported to have the best stability. Under bias conditions, and similar to silicon PV, potentially induced degradation, or PID, can occur. Degradation will be caused by alkali accumulation in the CIGS buffer layer and in the depletion layer, causing shunt paths and a lower VOC. Apart from moisture-induced and PID degradation, worm-like defects are found to be formed by exposing CIGS solar cells to reverse bias conditions. The left figure shows a microscope image of a cell with worm-like defects. Even propagation of such a defect is possible. On the right-hand side, we see a top view of a worm-like defect after chemical etching and the corresponding compositional analysis results. Close to the defect area, a rearrangement of elements was observed. Indium, gallium, and copper were replaced by cadmium, whereas selenium was replaced by sulfur. These worm-like defects act as local shunts, and depending on the concentration, they may permanently decrease the module output. Let us now discuss the impact of water ingress on module level and related to the degradation mechanisms described in the previous slides. Here we see a schematic drawing of the cross-section of a typical monolithic interconnection in a CIGS module. Multiple regions were reported to be vulnerable to degradation as well. P1 depicts the back contact scribe. If the CIGS material in the P1 scribe becomes more conductive, a shunt path in the module can be created, leading to a degradation of the module performance. P2 represents the second contact scribe, which builds the electrical contact between a molybdenum of one cell to the TCO of the next cell. Due to earlier mentioned molybdenum and TCO degradation, severe degradation in this scribe caused by oxidation can happen, causing significant power loss due to an increase in contact resistance. P3 is the isolation scribe. As mentioned, a non-conductive molybdenum oxide layer at the top surface of molybdenum can be formed, thus influencing the P3 area. In case the oxide layer becomes thicker, it can impact the lateral conductivity, resulting in a module degradation caused by a higher series resistance. In addition, we need to point out that the quality of the P1, P2 and P3 areas are not only influenced by the oxidation under damp heat test conditions, but also by the quality of the scribing processes. Of course, TCO degradation also significantly affects the module performance due to increased series resistance. Different from the CIGS case, for the amorphous silicon solar cell, the major degradation lies in light-induced degradation. The cause is the famous Stabler-Wronski effect, in short SWE, in the absorbing layer. Numerous studies and publications have focused on this subject. Under illumination, the weak silicon-hydrogen bonds in the absorbing layer were broken, leading to an increased density of defects. This causes an increase in the recombination current and reducing the efficiency of the solar cell. Such a degradation is well known to be recoverable after a post-annealing procedure. However, degradation happens again upon light exposure. To recap, today we talked about degradation in thin film PV cells and modules. For a CIGS solar cell, moisture-induced degradation occurs in all its individual layers. In a typical monolithically interconnected CIGS module, the back contact and interconnecting contact scribe areas can be vulnerable to degradation. For the isolation scribe area, degradation may occur in case the oxide is thick enough to impact the lateral conductivity. In addition, TCO degradation significantly influences both the cell and module performances. Unlike the CIGS case, the amorphous silicon solar cell is largely affected by light-induced degradation. It is well known to be caused by the so-called Stabler-Wronski effect in the absorbing layer. Note that there are various thin film PV technologies, including cadmium telluride and the emerging perovskite solar cells. For more information about their degradation analysis, please refer to the references as posted with this course.